My dear students, we will continue the complex numbers where we left in the previous class. So again, problem number 36. The roots of the equation x power x plus 1 whole cubed plus 27 plus 27 equal to 0 or 1 minus 4 minus 1 minus 3 omega minus 1 minus 3 omega square 2 minus 1 plus 3 omega and 4 1 minus 3 omega square 3 minus 1 minus 3 omega square 1 minus 3 omega minus 4 minus 4 1 minus 3 omega square and 1 plus 3 omega, where omega is a non-real cube root of unity. Cube root of unity. See, equations of this type we convert into the form x cubed minus 1 equal to 0 or x cubed plus 1 equal to 0 itself, because we know the roots of those two equations. So, if you convert this into x cubed minus 1 equal to 0, now the given equation can be written as x plus 1 whole cubed is equal to minus 27, and this we know that minus 3 whole cubed. So, that will give you that x plus 1 by minus 3 whole cubed is equal to 1, is equal to 1 itself. So, that means this is nothing but a capital X cubed is equal to 1, where capital X is minus of x plus 1 by 3, and you know that capital X is equal to 1 omega square, 1 omega and omega square. So, therefore minus of x plus 1 by 3 is equal to 1 omega square. So, this shows that, so therefore x is equal to, x is equal to minus 3 minus 1, that means minus 4, and minus 1 minus 3 omega and minus 1 minus 3 omega square. So, option is number 1. The answer is minus 4, minus 1 minus 3 omega, minus 1 minus 3 omega square. Here what you did is simply we have taken 27 to that side, which will become minus, and because cube is there and minus 3 whole cubed is minus 27. So, we can write as x plus 1 by minus 3 whole cubed is equal to 1 itself. So, which is nothing but in the form of x cubed is equal to 1, where capital X is minus of x plus 1 by 3, and you know that this represents cube roots of unity, whose values are capital X is equal to 1 omega square. So, therefore, x values are minus 4 minus 1 3 omega, minus 1 minus 3 omega, minus 1 minus 3 omega square. Problem number 37 is, if Z is complex such that mod Z is greater than or equal to 2, then the minimum value of modulus of Z plus half is 1 5 by 2, 2 belongs to 1 comma 2, and 3 5 by 2 greater than 5 by 2, and 4 lies between 3 by 2 and 5 by 2. Lies between 3 by 2 and 5 by 2. Okay? Right. Here, see, generally, what you do is, of course, many students and or many lecturers, they attempt this problem by taking Z is equal to x plus iy. But if you know little bit of this locus problems in complex organs diagram, then you can see that is mod Z is greater than or equal to 2 means all the points on the circle mod Z is equal to 2 and outside the circle This is the circle mod Z is equal to 2. That is radius 2. All the problems on the circle and outside the circle. It represents greater than or equal to 2. Means circle problems, the points lies on the circumference and outside the circumference. Okay. Now you know that because it is radius 2, so this is minus 2 0 point and this is 2 0 point. And you are given the mod Z plus half means is nothing but distance of Z belonging to the given region from the point minus half comma 0. So here so what is the minimum value? From this point, you take any point on the circle or outside the circle. If you join all these points to this point, and this is the point on this circle nearest to the point minus 2 0, because every other distance is greater than this distance. So mod Z plus half. So the minimum distance, so therefore minimum value of mod Z plus half is 3 by 2. Is a distance between minus 2 comma 0 and minus half comma 0, and the distance is nothing but 3 by 2. So here 3 by 2 is not there. So what is it? Right. The 3 by 2 value belongs to the interval 1 comma 2, because 3 by 2 is less than 2 and greater than 1. So it belongs to the interval 1 comma 2 itself. So option number 2. Actually, object type examination is very difficult. Unless you know the subject, one cannot get success in the objective type questions. If you know the subject very well and its applications, then here you need not do any working. They want only answer. So that's why if you are thoroughly well versed with the subject, you can use any technique and get the answer itself. If z is not equal to 1 and z2, if z2 is not equal to 1 and modulus of z1 minus 2z2 by 2 minus z1 z2 bar is equal to 2, is equal to not 2, is equal to 1, then z1 lies on number 1 on line parallel to x-axis, two line parallel to y-axis, and 3 circle of radius 2 4 circle of radius root 2. Z2 is not equal to 1 and this is modulus of this complex number is equal to 1. Then he is asking the locus of Z1, locus of Z1 itself. Right. Here please see, that is Z1 minus 2Z2 by 2 minus Z1 Z2 bar is equal to 1, means mod Z1 minus 2Z2 is equal to modulus of 2 minus Z1 Z2 bar. So that implies squaring both sides, or I will write squaring here itself. Why one more step? So this implies that Z1 minus 2Z2 into Z1 bar minus 2Z2 bar, because we know that mod Z whole square is always Z into Z bar is equal to 2 minus Z1 Z2 bar into 2 minus Z1 bar Z2. Minus Z1 bar Z2 itself. So now if you expand it and simplifying this one, you will get mod Z1 whole square minus 4 into mod Z2 whole square minus 1 is equal to 0. Just you simplifying and writing. If you want, I will write by simplifying and writing mod Z whole square is equal to Z into Z bar. But you are given that Z is not equal to 1. This cannot happen. So that implies that mod Z1 square minus 4 is equal to 0, or mod Z1 is equal to 2. So Z1 lies on a circle of radius 2. Therefore, Z1 lies on a circle of radius 2. And here if you want much more hypothesis I will give you. You take mod Z2 not equal to 1. So mod Z2 square minus 1 equal to 0 means mod Z2 is equal to 1. But you are given mod Z2 is not equal to 1. So therefore, mod Z1 square minus 4 is equal to 0. That means mod Z1 square, mod Z1 is equal to 2. So that means Z1 lies on a circle of radius 2 with center origin, itself. Answer is 3, option number 3. For this problem, slightly touches mains level. But it's a very good problem this is. Z1, Z2, Z3 are unimodular complex numbers. Unimodular complex numbers. Unimodular means modulus 1 complex numbers such that Z1 plus Z2 plus Z3 is equal to 1 and Z1, Z2, Z3 is equal to 1 and imaginary part of Z1 is less than imaginary part of Z2 and less than imaginary part of Z3. Then the integral part of Z1 plus Z2 square plus Z3 cubed, that is modulus, that is E is 1, 1, 2, 2, 3, 3, 4, 4. So that's why what I am saying, understanding this topic as it is different from understanding all the topics and mixing the topics in applications. That is required. Understanding topics and working problems, they meant for only you will get success in intermediate board examination. But in competitive examinations like EAMCET and MAINS and advanced level, all these they require the thorough knowledge of all the topics. Now by hypothesis, Z1, Z2 and Z3 are the roots of the equation Z cubed minus Z square plus KZ plus KZ and plus 1 is equal to 0. Because see, they are the unimodular and complex, they are the roots. Z1, Z2, Z3 are the roots of this equation because their sum is minus 1. And we know that the relation between the roots and the coefficients, which are thoroughly discussed in the, by my colleague, sum of the roots is simply minus of Z square coefficient by Z cubed coefficient. So, which is nothing but minus 1. So, if you can find the K value, then we are through. So, to find this, so by hypothesis what you get is Z1 plus Z2 plus Z3 is equal to 1 and Z1, Z2, sum of the product of the roots, Z2, Z3 plus Z3, Z1 is equal to K and product of the roots Z1, Z2, Z3 is equal to plus 1 is not, so it's minus 1 is equal to plus 1. So from this you have to find the value of K. You have to find the value of K itself. Sum of the roots is Z1 plus Z2 plus Z3, Z1, Z2 plus Z2, Z3 plus Z3, Z1 is equal to K and Z1, Z2, Z3 is equal to 1. Okay, right. Now you know that also mod Z1 is equal to mod Z2 is equal to mod Z3, each is equal to 1. Unimodular complex numbers. Unimodular complex numbers means modulus 1 implies Z1 bar is equal to Z2 bar is equal to Z3 bar, each is equal to 1. So therefore now we can have that is K is equal to Z1 Z2 plus Z2 Z3 plus Z2 Z3 plus Z3 Z1 by Z1 Z2 Z3. Of course, I don't go beyond this because Z1 Z2 Z3 value is 1. So this is nothing but 1 by Z1 plus 1 by Z2 plus 1 by Z3. But 1 by Z1 is Z1 bar and 1 by Z2 is Z2 bar, 1 by Z3 Z3 bar. So this is Z1 bar plus Z2 bar plus Z3 bar. So this is Z1 plus Z2 plus Z3 whole bar, which is equal to 1. So therefore K value is 1. So therefore K is equal to 1, so that the equation is Z cubed minus Z square plus Z minus 1 equal to 0. What you are given is common, and for this the roots are, this we can written as Z minus 1 into Z square plus 1 equal to 0. That is Z cubed minus Z square plus Z minus 1 if you expand it. So this shows that therefore Z is equal to 1 and Z is equal to plus or minus I, because Z square is equal to plus 1, minus 1 means Z is equal to plus or minus I. So therefore Z1 you can take it as, and you are given that imaginary part of Z1 less than imaginary part of Z2 less than imaginary part of Z3 implies, Z1 is equal to minus I, because imaginary part is this one is not minus 1 minus I, and Z2 is equal to 1 and Z3 is equal to plus I. Z1, the roots are 1 plus or minus I. Now how to choose Z1, Z2, Z3? Understand? We know the roots Z1, Z2, Z3 in a total, but how to distinguish which is Z1, which is Z2 and which is Z3? So for that, the further image hypothesis you have to use this one. Imaginary part of Z1 less than imaginary part of Z2 is less than imaginary part of Z3. Here for Z1, if you take 1, imaginary part is 0. If you take minus I, imaginary part is minus 1. And you know that minus 1 is less than 0. So this implies that Z1 is equal to minus I, Z2 is equal to 1 and Z3 is equal to plus I. So now you can write, so therefore modulus of Z1 plus Z2 minus Z3 plus Z2 square and Z3 cubed is equal to Z1 minus I, Z2 plus 1 and Z3 whole cubed is minus I. So which is 1 minus 2I. So this is nothing but the square root of 1 plus 2 square, which is root 5. Its integral part. So therefore, integral part of mod z1 plus z2 square plus z3 cubed is simple integral part of root 5, which is 2, which is equal to 2 itself. So the answer is, which one, which option? Number 2, option number 2. Option number 2 answer. So here, please see, here you have completely used that properties of relation between the roots and coefficients of an equation. So for that we have obtained z1, z2, z3 values, the roots of the equation, namely 1 plus or minus I. Now to distinguish, because he has given modulus of, asked modulus of z1 plus z2 square plus z3 cubed. So this modulus depends on the numbers. So therefore, how to judge which is z1, which is z2, which is z3? For that, you use the information, imaginary part of z1 less than, imaginary part of z2 less than, imaginary part of z3. So imaginary part of minus I is minus 1. And imaginary part of 1 is 0. So minus 1 less than 0. And 0 less than plus 1, which is I, imaginary part of I. So z1 is simply, z1 is minus I, z2 is 1 and z3 is plus I. So now modulus of z1 plus z2 square plus z3 cubed is, so minus I plus 1 minus I. So that is 1 minus 2I modulus, and which is root 5, and root 5 integral part is 2. Or now you can see that is, what is the problem number? 40. Square 40 problem number. Now you can write it. If modulus of z plus 2 by z is equal to 2, then the maximum value of, then the maximum value of mod z is 1 root 5 minus 1, 2 root 5 plus 1, 3 root 3 minus 1, and 4 root 3 plus 1. Modulus of z plus 2 by z is equal to 2, then the maximum value of mod z only is asking. Right. So solution is simply, you know that mod z is equal to modulus of 2 by z minus 2 by z. And you know that this is less than or equal to modulus of 2 by z plus 2 by mod z. 2 by mod z. But this is, you are given 2. So 2 plus 2 by z itself. This is modulus of z1 minus z2 is less than modulus of mod z1 plus mod z2. Okay, right. So this shows that implies mod z square minus 2 mod z minus 2 is less than or equal to 0. That means, therefore, mod z should lie between the roots, and this topic also is covered by my colleague in the previous classes, should lie between the roots of the equation mod z whole square minus 2 mod z minus 2 is equal to 0. That is, mod z lies between lies between 2 plus or minus square root of b square minus 4ac means 4 plus 8 by 2a, namely that is 1 plus or minus root 3. That implies 1 minus root 3 less than mod z, and this is less than or equal to 1 plus root 3. Because here equal to 1 cannot happen, because 1 minus root 3 is negative, but mod z is always positive. So the maximum value is 1 plus root 3. The maximum value is simply root 3 plus 1. Root 3 plus 1. If ax square plus bx plus c, the quadratic expression is less than 0, less than or equal to 0 means that quadratic expression must lie between its roots. The roots, say alpha and beta, the value of that expression must always lie between that alpha and beta itself. So here alpha and beta are 1 minus root 3 and 1 plus root 3. Now this is 41. If log basis root 3 of mod z square minus mod z plus 1 by 2 plus mod z is less than 2, then z lies on 1, a straight line through the point through the point 1 comma 1, 2 on a circle with radius 4, and 3 lies on a circle lies inside a circle with center origin, with center at 0, 0 and radius 5. And 4 lies outside a circle with radius 5 and center 0, 0. Now here you know that the base is root 3, which is greater than 1. So the given inequality implies if and only if mod z whole square minus mod z plus 1 is by 2 mod z, 2 plus mod z is less than root 3 whole square, which is equal to 3 itself. So that if and only if z square mod z square, please see, mod z square minus mod z plus 1 is less than 6 plus 3 mod z. So that is if and only if mod z square, okay, if you come to here minus 4 mod z minus 5 is less than 0. So that indicates that this you can write as mod z minus 5 into mod z plus 1 is less than 0. And mod z plus 1 cannot be less than 0. Less than 0 means either one of them is negative and one of them is positive. But mod z plus 1 cannot be negative. It cannot be negative. So this should be negative. So this if and only if mod z is less than 5 and since mod z plus 1 cannot be negative. So therefore, z lies on a circle, inside a circle with center origin and radius 5. Please see, mod z less than 5 means what it is? That z point lies inside the circle with center origin and radius 5, because it's not equal to 5, it's less than 5. So inside the circle. So the option is with center at origin and radius 5. So 3. So because the complex numbers problems may be clubbed with logarithms also. So to make a point that complex, see, any topic problems can be clubbed with any other topic. 42. This is a very good problem. It's a good problem. The number of non-zero complex numbers. Complex numbers for Z satisfying Z bar is equal to IZ square is 1, 2, 2, 4, 3, 3 and 4, 6. Right. So now solution is let ZB is equal to x plus IY, so that Z bar is equal to x minus IY and Z square is x square minus y square plus I into 2xy. And you know that Z bar is equal to I into Z square implies real parts are equal and imaginary parts are equal, implies x is equal to 2xy and x square minus y square is equal to y. X square minus y square is equal to y itself. Okay, right. Now x is equal to 2xy implies either x is equal to 0 or y is equal to 1 by 2. Now x is equal to 0 implies y square is equal to y, that implies y is equal to 0 or y is equal to 1, y is equal to 1 itself. But z is not equal to 0, 0. Z is not non-zero complex numbers. Z is not equal to 0, 0 implies, so x is equal to 0 and y is equal to 1. That implies z is equal to I, 0, 1. Right. Now you could go to the second part, second case. So now x is not equal to 0 implies you can divide by x, implies y is equal to 1 by 2, so that x square minus y square is equal to y implies x square minus 1 by 4 plus 1 by 2 equal to 0. So that implies x is equal to plus or minus half. So therefore, the required complex numbers are z is equal to y, and when x is not equal to 0, then what you will get is y is equal to this one, x is equal to. So 1 plus I by 2 and 1 minus I by 2, because x is equal to plus or minus half when y is equal to half. So there are similarly three complex numbers. There are three complex numbers satisfying that equation. X is equal to 0. Please see once again, I will explain it is x is equal to 2xy and x square minus y square is equal to x square minus y square. Here we did a mistake. X is equal to minus 2xy, because what is the equation you got? X minus iy is equal to x square minus y square minus 2ixy. This is implies, so just I repeat, the number of complex numbers same, but complex numbers are different. Please see, x minus iy is equal to I into x square minus y square minus I into 2xy. Implies this I, that means z square. So this is either, that implies either x is equal to 2xy or y is equal to, this is minus y is equal to x square minus y square, right. The number of complex numbers is same. So this shows that x is equal to 0 or x is equal to or y is equal to half. X is equal to 0 implies when x is equal to 0, you will get y square is equal to y. So that implies either y is equal to 0 or y is equal to 1. But z is not equal to 0, 0. Implies x is equal to 0 and y is equal to 1. That implies z is I, 0, 1. Now when x is not equal to 0, implies y is equal to half. Y is equal to half. So therefore, x square minus y square is equal to minus y implies you will get x square minus 1 by 4 and y is equal to minus half. So this is y is equal to half. So plus 1 by 2 equal to 0. So that means it's okay. X is equal to x square is equal to 1 by 4 or x is equal to plus or minus half. So what we did is correct. So therefore the number of complex numbers is 3. Right. Next problem is this. If z is complex, this is problem number 43. If z is complex, then the minimum value of mod z whole square plus mod z minus 3 whole square plus mod z minus 6i whole square is 1, 15, 2, 30, 3, 20 and 4, 40. Now you can see that is let z is equal to x plus iy. So that mod z whole square plus mod z minus 3 whole square plus mod z minus 6i whole square is equal to x square plus y square, x square plus y square plus x minus 3 whole square plus y square plus x square plus y minus 6 whole square, y minus 6 whole square, that is 3 into x, you multiply it, 3 into x square plus y square, I will tell you, 3 into x square plus y square minus 6x minus 12y plus 15, plus 15 you will get. Here minus 6x you will get plus 9 plus 36. So plus 9 plus 36 means 45. Sorry. Okay. So this we can write as 3 into x square plus y square minus 2x minus 4y plus 15. So 3 into 15, how much you will get? You got plus 5, sorry, plus 5. So 15 is over, so you will get plus 30, plus 30. Now this is nothing but 3 into x minus 1 whole square plus y minus 2 whole square plus 30. And you know that this is always greater than or equal to 30. It's always greater than or equal to 30 and equal to 30 when x is equal to 1 and y is equal to 2. It's always greater than or equal to 30, equal to 30 when x is equal to 1 and y is equal to 2. So therefore the maximum value, max value of the given is equal to 30. So which is problem number, that is solution, option number 2. Please here just algebra. We have nothing, we have not used any techniques. Just you write z is equal to x plus iy, then this expression becomes this. Now from this what you get is 3 is common, we have taken 3 into x square plus y square minus 2x minus 4y plus 5, that means 3 into 15. So the remaining one is 30. But this expression is nothing but x minus 1 whole square plus y minus 2 whole square plus 30. So this is greater than or equal to 30 and equal to 30 if and only if x is equal to 1 and y is equal to 2. That means the complex number 1 plus 2i. Problem number 44. If mod z1 minus 1 less than 1, mod z2 minus 2 less than 2 and mod z3 minus 3 is less than 3, then mod z1 plus z2 plus z3 1 is less than 1, 2 greater than 6, 3 less than 12 and 4 lies between 6 and 12. Modulus value. So now we take up modulus of z1 plus z2 plus z3 is equal to modulus of z1 plus z2 plus z3 minus 6 plus 6. So add and subtract 6. Because why, how you got that idea? Here 1, 2, and 3 are there. So 1 plus 2 plus 3 is 6. So subtract 6 and add 6. And this you know that modulus of Z1 minus 1 plus Z2 minus 2 plus Z3 minus 3 plus 6. That 6 we have adjusted 1 for Z1, 2 for Z2 and 3 for Z3. And this is less than or equal to mod Z1 minus 1 plus mod Z2 minus 1 minus 2 plus mod Z3 minus 3 plus 6. Because modulus of the sum is less than or equal to sum of the moduli. And this is nothing but 1 plus 2 plus 3 plus 6, which is equal to 12. So less than 12. So sometimes suppose you take Z1 is equal to 1, Z2 is equal to 2, Z3 is equal to 3, then this will be 0. 0 plus 6, 6, which is less than 12, which is less than 12 itself. So even that also satisfied. I promise you that we will do in the course of the discussion, we will find the value of omega power n plus omega power 2n plus 1 value. Now I am doing that one. Let omega not equal to 1 be a cube root of unity. And n is a positive integer. N is a positive integer. Then 1 plus omega power n plus omega power 2n value is number 1, 0 or 3, 0 only, 3 only, and 4 is 1. So you can see that we can write n is equal to some 3k or 3k plus 1 or 3k plus 2, because when a positive integer n is divided by 3, the remainders must be either 0 or 1 or 2. So remainder 0 when n is a multiple of 3, and remainder 1 when n is of the form 3k plus 1, and remainder 2 when n is of the form 3k plus 2. So now you can write that is, now if n is equal to 3k, then 1 plus omega power n plus omega power 2n is equal to 1 plus omega power 3k plus omega power 6k, which is 1 plus 1 plus 1 is equal to 3. Now n is equal to 3k plus 1 implies omega 1 plus omega power n plus omega power 2n is equal to 1 plus omega power 3k into omega plus 1 plus, that is plus omega power 6k into omega square, So this is nothing but 1 plus omega square again, which is 0. Similarly, if n is equal to 3k plus 1, then 1 plus omega power n plus omega power 2n is of the form 1 plus omega square plus omega, which is 0 again. So in any case, this 1 plus omega power n plus omega power 2n is either 0 or 3. If it is 0, it is 0. If n is not a multiple of 3, is equal to 3 if n is a multiple of 3 itself. So this value is always 0 or 3. So, okay. In the next class, again some more problems, and then we will come to the geometry, other properties of complex numbers, namely geometry of complex numbers, which is very, very important, even though not so much in EAMCET, but in the other examinations. But if you use geometry of complex numbers, you will feel how easy the complex number chapter.